Unraveling Recursive Algorithms with Divide and Conquer Strategies. The world of computing thrives on elegant solutions to complex problems, many of which are elegantly captured by recursive algorithms. By breaking down large tasks into smaller subproblems that resemble the original, recursion offers an intuitive approach that aligns with human problem-solving patterns. At their core, recursive algorithms rely on two fundamental principles: base cases that halt recursion when reached, and recursive steps that reduce larger instances toward these bases. This framework enables programmers to tackle challenges ranging from sorting algorithms to graph traversal efficiently and beautifully. Fundamentals of recursive function design. A well-crafted recursive function must always define clear stopping conditions known as base cases. These act as safeguards against infinite loops while ensuring computations terminate at predictable points within the solution space. In contrast to iterative counterparts that use loop variables explicitly, recursive functions often encode state information through parameter values themselves. For example, calculating factorial n becomes possible via n asterisk factorial n1 until reaching 0, where multiplication yields identity element 1. Base case definition establishes termination condition, typically handles smallest possible input size reductive step, decomposes current problem into simplified version applicable for further recursion calls. Argument adjustment ensures progressive movement towards resolving underlying subproblems. Effectively, mechanics behind stack-based execution. Every time a recursive call is made during program execution, memory allocated inside function scope gets temporarily stored onto the system stack. Data structure. When subsequent calls return results back upwards through activation records they've created along execution path. This last in first out, LIFO, behavior ensures correct sequence of operations even though multiple levels of nested function invocations may occur simultaneously without risking mismatched computation flows. Simplified view. Imagine stacking plates sequentially in dishwasher tray before cleaning them off backwards following exact order placed initially. Although efficient conceptually, excessive depth can lead to stack overflow errors exceeding available memory limits set by operating systems. Understanding how much headroom remains between lowest-level function call locations matters significantly in practice scenarios. Classical examples illustrating core concepts. The classic Tower of Hanoi puzzle demonstrates perfect application domain for exploring power of divide and conquer philosophy embedded inherently within recursion principle itself. By reducing moving n disks requirement progressively down to n equals 1 situations solvable trivially through direct relocation methods without additional constraints. Tower of Hanoi, an archetypal demonstration with 3 pegs labeled source, S, auxiliary, A, destination, D. Solving Tower's challenge involves clever strategic moves redistributing disk positions systematically according to rules specified. For any number n greater than 1 requiring transfer, process divides naturally occurring task components across different spatial regions leveraging intermediate storage capabilities uniquely offered through spare location provisions. An illustrative breakdown would show step-by-step migration sequences highlighting pattern emergence, facilitating deeper comprehension among practitioners seeking mastery over such techniques. Optimization tip: modern implementations prefer using bit manipulation rather than traditional procedural approaches whenever dealing huge numbers because computational complexity decreases sharply from O(2 to the power of n-O, n). Binary search. A logarithmic advantage beyond theoretical abstractions found commonly associated with puzzles lies practical applicability demonstrated extensively in binary search operation performed routinely within diverse contexts like database querying. Data structures. Maintained sorted allow searching through repeatedly having unsearched segments, thereby maintaining O, log n, performance characteristics consistently regardless dataset volume variation factors present. Implementation follows precise procedure involving setting upper/lower bounds and comparing middle elements' relative target value, seeking successful match identification outcomes. Fractal generation using recursive patterns growing tree-like structures such Mandelbrot sets utilize repeated applications mathematical transformations generating intricate visual compositions exhibiting self-similarity traits inherent. natural phenomena around us. Each iteration applies small adjustment changes propagating through successive layers, forming progressively denser complexity patterns observable at varying magnification scales. Coding implementations frequently involve drawing commands incorporated within loop constructs controlling depth limits, regulating overall image resolution quality obtainable under given hardware resources constraints. This technique also finds uses elsewhere, including generating maps displaying terrain elevation features appearing chaotic but containing subtle organizational regularities beneath superficial randomness impressions. Dynamic programming integration opportunities. While basic form recursions often suffer repeated calculation overhead due redundant work resubmitted earlier stages already resolved successfully without necessity reprocessing same inputs twice. To optimize efficiency trade-off between extra memory consumption required storing computed answers versus potential gains derived from eliminating wasteful recomputation cycles. Classic Fibonacci series serves excellent demonstration showing difference between naive exponential runtime versus optimized linear improvement achieved merely adding memoization caches layer functionality. Memoization techniques for enhancing performance technique called caching or memoizing consists retaining previously calculated outputs allowing immediate access whenever identical parameters reappear, ensuring elimination unnecessary duplication efforts previously undertaken. Different variations exist implementing either bottom-up dynamic table construction mechanisms, alternatively top-down strategies augment existing recursive code bases, preserving functional integrity while improving asymptotic complexities dramatically. Comparative analysis between iteration and recursion iteration provides explicit control flow management, making debugging exercises somewhat straightforward compared alternative counterpart whose hidden operational mechanics remain obscure unless carefully inspected manually. Purists argue preference depends heavily contextual requirements considering factors surrounding both resource usage limitations imposed by particular environments plus programmer expertise level. Sufficient understanding involved nuances entailed. Evaluating space-time trade-offs. Recursively implemented versions generally require higher memory footprints due proliferation stack frames generated each invocation consuming precious limited capacity provided modern processors manage. Conversely, iterators tend to consume less heap storage, allocating temporary variables managed automatically releasing once operations complete, unlike counterparts whose scopes persist longer depending call stack configuration details. Therefore, judicious choice based upon situation specifics, including acceptable delay tolerances, users ready encounter waiting extended periods possibly caused heavy recursion tree development paths exhausting available capacities prematurely. Linguistic abstraction layers influencing expressiveness. Functional languages such Haskell naturally support recursion without relying mutation primitives. Common imperative paradigms typically necessitate managing side effects consciously avoiding unintended consequences impacting reliability. Crucial safety assurances required production-grade software deployments. Type inference features assist maintain clean readable code styles. Preventing accidental bugs arising. Messy global state manipulations frequently encountered imperative codebases, especially those handling concurrency models appropriately isolating thread interactions properly synchronized correctly. Cognitive load implications during problem-solving phases. Novice developers often struggle grasping recursive mindset. Fundamentally distinct procedural orientation acquired traditionally learning computer science fundamentals usually emphasized stepwise incrementality progressions. This paradigm shift demands mental flexibility, adopting reverse engineering perspectives, working backwards, deducing solution pathways originating end goals, rather forward designing implementation routes, expecting incremental constructions, building blocks leading final outcome destinations successfully. Teaching strategies for effective pedagogy. Experienced instructors employ various visualization tools illustrating call stacks progression, visually depicting expansion, followed eventual contraction phases mirroring physical motions akin opening/closing folders, directories, explorer windows, offering tangible references, grasp abstract concepts easier intuitively. Careful selection. Canonical examples chosen represent wide spectrum difficulty ranges catering beginners, intermediate, experts alike, ensuring curricula coverage breadth necessary, cultivating robust foundational knowledge, eventually enabling transition advanced topics seamlessly. Interactive coding platforms supplement lecture materials, giving students opportunity practicing actual writing, testing, reading, debugging real-world problems, reinforcing learnings retained effectively. Emerging trends shaping future developments. Current research explores parallel processing opportunities, unlocking latent capabilities, distributed systems capable executing independent branches concurrently, enhancing performance considerably beyond sequential execution capabilities. Restricted single-core architectures. Historically dominant mainstream computing landscape thus far predominantly. Advancements continue evolving, making cloud-based infrastructure viable options, deploying scalable microservices, requiring minimal upfront investments, realizing benefits realized sooner, faster than ever before achievable, otherwise requiring significant capital expenditures. Traditionally associated enterprise-level operations, formerly exclusive corporate entities, only accessible privileged organizations. These innovations suggest continued relevance, field promising rich avenues, exploration, investigation ahead, upcoming years shaping next-generation technological revolutions, forthcoming decades ahead, eagerly anticipated entire sector. Community engaged, passionate pursuit, innovation, breakthrough discoveries, tomorrow's milestones, today's achievements becoming. Conclusion: recursive algorithms have proven invaluable across disciplines, transforming challenging problems into manageable pieces through strategic decomposition methodologies grounded solid theoretical foundations, backed empirical validations. Demonstrating effectiveness, repeatedly tested, proven, reliable, versatile, adaptable frameworks, applicable countless scenarios imaginable, conceivable. Developers embracing this powerful abstraction gain ability, think differently about design choices, fostering creative solutions previously unimaginable, expanding boundaries, what technically feasible, pushing envelopes, continuously driving advancement fields we depend daily.